remember what we did on what day. Alright, plan for the week. No one is playing from home, so we can skip on real quick from that. I did not get your guys' masteries graded. Sorry. Actually, my neighbor's impromptu invited us over yesterday evening because he's like, it's such a lovely evening. Do you want to come over? They're new, right? They just moved in, so we're still trying to get to know them. So
he said, no, I don't know you.
I said, no, I have reading to do. No, we went over this one. So 1 through 4 as the highest roll.
I feel like that number is not important.
That goes to player 1. It's a player 1 victory. 5 and 6 is a player 2 victory. And we're rolling 2 dice, right?
4 dice.
2 dice.
No, it's 4.
It's 4 dice. It's 2 dice each, but it's 4 dice. It doesn't really matter who's rolling the dice. It's 4 dice, because each person rolls 2 dice. Also, why do you have dice on a dozen?
Every time I go sailing, I take dice with me.
In case you get stranded?
Yeah.
You and a fellow castaway are stranded on a desert island, playing dice for the last banana. You've agreed on these rules. You'll roll 2 dice, and if
You'll roll 2 dice.
Okay,
base number is 1, 2, 3, or 4.
Yeah, they just
player 1
put 4 dice there to show it.
If the biggest number is 5 or 6, player 2 wins.
I don't want to say I told you so, but I told you so. I don't know.
Definitely changes the probability.
Why would that change the probability?
Because for player 1, all of them have to be 4 or under for them to win. So it's dependent on the other ones. It's dependent probability. Whereas for 5 and 6, any of them are 5 or 6, player 2 wins. So it's independent.
How would we model that?
So for the 1, 2, 3, 4, I did 2/3 times 2/3. Because there's a 2/3 chance it'll be between 1 and 4.
So is that for each pair of dice?
No.
What if I? Oh, for the 2, so like die 1, die 2.
Yeah.
So we'll give it to me. So it's 4, 6 really. I'm gonna work unreduced just because we're talking dice. I like to be unreduced at first. So you said 4, 6 times 4, 6.
Yeah.
Because 1, 2, 3, 4. 1, 2, 3, 4.
Yeah. Both of them have to be.
Okay.
For
Now
player
wait. Yeah. Okay.
And then for player 2, if either of them is 5 or 6, then
So the chance of 5 or 6 is a 2, 6
2, 6 plus 2, 6.
plus. Why plus? Oh, because or.
Yeah, either of them are.
Oh, so this is like an and. So I need a 1 through 4.
And a 1 through 4.
Yeah, and not an or because I have to have both of these be low, kind of, I guess. I would kind of call this low.
So, yeah.
And this one high. So I need low and low. Really just say low because this looks like 1 minus 4. Now that's the weird thing. And makes us multiply.
That 4 makes us add.
When and used to tell us to add, right? When we're in like simple math classes, and tell us to add. But okay, so here we multiplied, and now you're saying that we should add?
For that one,
Is there, what if that doesn't make sense to me? Is there a way that like I could draw my way to there? This chair is squeaky. Because I don't know if that's still, because does this add up right? This is 2/3 plus. Is that a third? I don't think that's a third.
no, that's 4 nines.
Wait,
I
what?
want both of them win on either of my decks.
I think somebody always wins. You said this reduces to 4 nines. I got you. I'm with you. So wait, we have too much probability here. Right? Crap. So this isn't right, but I'm going to leave it up here for a second. I'm not a fan of like instant erase. I actually really, as you guys get deeper in math, I want to encourage you to like, don't erase wrong work because it's worth staring at to try to figure out what happened.
Well, I think I figured it out not using math.
Okay. We're all listening.
I just drew a diagram.
Tell me more.
So I put like 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, and then I marked which ones player 1 wins and which ones player 2 wins. And then I got 20 out of 36 player 2 wins and 16 out of 36 player 1 wins.
Oh, that is a good idea.
That's how they did it
Don't
on
sound so
Academy.
surprised.
That's on
Sorry, that's what I always tell people when they say that I had a good idea because they always sound surprised. I'm like, wow.
Why do you put the little like 2 lines for the 1?
What other symbol do we use in math that looks an awful lot like a 1?
Absolute value.
Absolute value.
And parallel lines.
So I used to confuse myself when working with absolute value, so I started making my 1s and my 7s fancier.
Yeah, I always make 7s like with the line through them.
Alright, now we're going to get fun since we're on the smart board. What would you like to represent player 1 out of the option of stars, smiley faces, flowers, rainbow? Okay. So wait, player 1 wins
1-1.
here,
Can you check it?
here. Sure.
All of, I think, yeah. Oh, no, but not the next one. Yeah. In like a square. Player 2 is my color.
What do you want player 2 to be?
Star.
It doesn't check as
Oh,
well.
that looks.
Wait, hold on. Hold on. We got it.
Yay.
That was like really weird.
Oh, it's like a weird looking caterpillar.
I was thinking cactus.
I was thinking
Like a little plant.
Oh, yeah.
I was thinking like spiky weapons and that.
So wait. Why? What went wrong up here? Can we figure that out from down here?
Well, the 2 6 times 2 6 is
Plus.
2 6 times 2 6 or 4 6 times 4 6?
or
It becomes
the 4 6 times 4 6.
right?
Wait, so this comes out to be the same as what we had said.
Yeah, because it's just 4
Yeah.
times
Well, come on. Give me something better. Will you not let me go smaller with this? No, you won't. Wow. Okay.
In thick pen.
4. I think Jake was like that. It
All right, so that's 4 6 times 4 6.
Yeah.
How?
Well, it's the difference of the total because like someone always has to win. That's how I did it. Or I just counted.
Honor smart and I'm not.
So wait, we've got those. Let's say there's like a red die and a blue die,
Okay.
right?
Yeah.
Or there's like
A pink die.
A whatever. Very red.
a that die and a this die.
Oh, that would
Oh,
just
that
not show
looks
up
cool.
well.
That looks really weird from the side. Looks like somebody took paint and like taped it off and then like spray painted.
Yeah.
All right, back on topic. So wait, when this die gets a 5 or a 6, it trumps out no matter what that die has. And if this die gets a 5 or a 6, it trumps out what the other die does.
But they oversect.
Wait a minute.
Overset.
Whoa.
Intersect, yeah.
Overlap?
Overlap, yeah. I mixed 2 words.
Flowers.
But right here, right there, What did we do?
Both of them got a 5.6.
Ooh, we counted it twice. So this brings in this idea in math that we call.
Oh, it's got it.
Can I get smaller? Oh. Can I get any smaller? Oh.
That could probably get it down.
Over.
Nope.
No, like that. Come on. The stars are just special. Calculate?
Yeah, overcounting. Let's write that down so we know. That was not a good way to write down any notes. Oh, we should go back and see the end of the video.
Yeah, we should.
I think player 2 has the advantage.
Yeah.
Isn't that what we figured out?
Yeah.
Let's try twice more. Here, player 1 wins. And here, it's player 2. So who do you want to be? At first glance, it may seem like player 1 has the advantage, since she'll win if any one of 4 numbers is the highest. But actually, player 2 has an approximately 56% chance of winning each match.
So it's not hard.
One way to see that is to list all the possible combinations you could get by rolling 2 dice, and then count the ones that each
But
player
that's
wins.
silly.
These are the possibilities for the yellow die. These are the possibilities for the blue die.
So what I'm commenting would be silly is listing out 1, 1, 1, 2, 1, 3, 1, 4, 1, because that would be silly. So always a table like this is a better idea. This is mathematically known as an area model.
Oh, yeah, we do this in
Disgusting.
homework.
See,
For a time.
I like when you guys are like excited about things because normally vocab words because you're like, meh, whatever. But yeah, area models are really useful, right? They're an amazing tool. I will admit, hi, my name is Micah Hudson. I have a problem with math addiction. I will admit I've done an area model to calculate probabilities on a board game to like decide what are better, like if this goes with it, like it makes sense when two, like, so wait, when we thought it was 4 dice, would this work?
If you measure four dimensions,
Jake, you with us? I think you're in my posters. If we had 4 dice, let's even say if we had 3 dice, would an area model work?
It would. It would be more complicated.
You'd have to
What do
make
you-
like a 3-dimensional one.
Ooh, it would have to be like a
It'd have to be like a cube that you
Yeah.
can see inside.
like a volume model.
Yeah.
If this is an area model, would that be like a volume
Yeah.
probability model? So then wait, would 4 work?
Like in theory?
In
Yeah.
theory.
In
There's
theory.
no way to,
That's
like,
such a dangerous word to use.
Try.
In
Because
theory.
you don't, like,
There's no way to measure it.
Okay, we should get out of the rabbit hole.
Each cell in the chart shows a possible combination when you roll both dice. If you roll a 4 and then a 5, we'll mark a player 2 victory in this cell. A 3 and a 1 gives player 1 a victory here.
I think this is why they did
There
a
are
cat.
36 possible combinations,
It's easy.
each with exactly the same chance of happening. Mathematicians call these equiprobable events. Now we can see why the first glance
Why, so equal probable events. Why in this situation, like the players aren't equally likely to win, but why are these events equally likely?
Because they're independent of each other.
Yeah, I like that. I wasn't even thinking that, but yes. And the dice are fair, right? So a lot of times we preface these problems with a set of fair dice or a fair number cube or whatever. So like if you go to a casino, why are you chuckling?
Because some casinos are done crowded with dice.
Well, okay, even not even thinking about dice. I mean, yes, good point. What other casino games are there? I mean, you guys are like
Slots.
14, so I just like
Poker.
who? What? What is craps? No, I know what craps is, but what is craps? Okay, it's a dice rolling game, so that's still dice. But do you know how you bet in craps? Okay, it's not very complicated. It's relatively complicated. You're betting on like the outcome of things. You're betting either like with the house or against the house. You really want to bet against the house because if you bet with the house, you're betting that everybody else at the table loses. There's a lot of like kind of moving parts in it. But like a roulette wheel, right? Is green equally likely to red or black?
No, it's like 1 on the thing.
Yeah, it's like 1 on the thing, right? But red and black are probably equally probable events. All right, so sorry, we keep going down rabbit holes.
Even
My
though
fault.
player 1 has 4 winning numbers and player 2 only has 2, the chance of each number being the greatest is not the same. There is only a 1 in 36 chance that 1 will be the highest number, but there's an 11 in 36 chance that 6 will be the highest. So if any of these combinations are rolled, player 1 will win, and if any of these combinations are rolled, player 2 will win. Out of the 36 possible combinations, 16 give the victory to player 1, and 20 give player 2 the win. You could think about it this way too. The only way player 1 can win is if both dice show a 1, 2, 3, or 4.
So
A 5 or
and
6 would mean a win for player 2. The chance of one die showing 1, 2, 3, or 4 is 4 out of 6. The result of each die roll is independent from the other, and you can calculate the joint probability of independent events by multiplying their probabilities. So the chance of getting a 1, 2, 3, or 4 on both dice is 4 out of 6 times 4 out of 6, or 16 out of 36.
the stop motion yarn.
Because
Yeah.
someone has to win, the chance of player 2 winning is 36 out of 36 minus 16 out of 36, or 20 out of 36. Those are the exact same probabilities we got by making our
I
table.
mean,
But
sure.
this doesn't mean that player 2 will win, or even that if you played 36 games as player 2, you'd win 20 of them. That's why events like dice rolling are called random. Even though you can calculate the theoretical probability of each outcome, you might not get the expected results if you examine just a few events. But if you repeat those random events many, many, many times, the frequency of a specific outcome, like a
Anyone know what this is called? The mathematical thing that says if you do this a bunch of times, it's gonna be true. Like, so if I roll dice 36 times, like he just said, I'm not necessarily gonna get 20 player 2 wins. But if I roll them 3,600 times, I should be very close to 200. Right? If I multiply both of them by 10. And if I do it 36,000 times, I should be extremely close to 20,000.
No, you're going to count by multiple times.
No, well, this does matter. This, and you could write it down, you might just remember it, is called the law of large numbers. I love that they call it a law.
Really? They call it the law of
The law of large numbers.
What was overcounting again?
We're going to come back to that. I'm going, don't worry. I'm watching the clock very diligently to make sure I have time to loop back. I like teaching you guys a bit more freeform.
Brad.
Not sporadic. This is planned. It may not seem like it. So the law of large numbers says if I do something a ton of times, it's likely going to come true. Here's the problem. Casinos know that. So, games are designed that, like, to be able to play to the law of large numbers, you don't have time or they mess with you. So, if you're playing blackjack or poker or any deck card game, you know what they do?
They like take a card out or something?
So, any deck draw card game, like blackjack, you draw cards from the deck, and if you know what card counting is, it's actually keeping track of the running probability. I'm not telling you to go to casinos. I'm not telling you to gamble. What I am telling you is it's rigged against you, so you will lose money.
I read Bring Down the House.
Yeah, it's such a good book, right? So the problem is you'd have to stay there for a very long time for it to come true and let the deck, like, go through the probability. And they swap out, they actually put, like, 8 decks together, shuffle them all together, and they swap them out, like, a third of the way into the stack to fight you being able to play the probability. Yeah, I'm not quite sure. And different casinos probably do it
Is
differently.
it possible still to play the probability?
You can still do card counting. It's just not as reliable because the sample set is so large. Sorry, what was that, Jake?
I said that's what they did in that book. They made like $3 billion.
Yeah. So what they would do in the book, I don't want to spoil it. Do you want a spoiler or no?
What's the book called?
Bringing Down the House.
Never heard of that.
One of my students is reading it right now. Unless he's done. He might have finished it. I think he might have finished it. Do you have a book that you're reading right now?
Me?
Yeah.
I'm reading Lord of the Rings.
You can read that anytime. Let me see.
Yeah, but I don't want to read it. So I.
Let me see if Franco is done. You want a different book?
No.
Bringing Down the House is pretty
I
sweet.
really should read Lord of the Rings.
So, law of large numbers says if you do this for a long time, things should come true. The casino fights against it by messing that up, by making the sample size really, really big, and then yanking the rug out from under you, not even halfway into the sample size. Of course, I broke my speaker. I don't know why this happens. Oh, I think it has something to do with that microphone. Alright, so here's the issue, though. We just did this. We tried to do the math, and we overcounted. So let's go a little bit simpler here and see if we can figure out how to fix our overcounting issue. So there are certain genetic traits to tell a fun story about myself. When we were trying to figure out my heart issue, one thing they looked at was, do I have Marfan syndrome? Which at first I thought they said Martian, like Martian. I was like, wait, what? Say that again? Yeah. So I was like, wait, can you repeat that and tell me if you think I'm an alien? It's like where your appendages are really long and certain things like that. It's a genetic thing which would help them try to track down like my heart issue. I am not a Martian. It is okay. But one genetic trait is if you can bend your thumb backwards.
Oh yeah, my dad has like hitchhiker.
That's what it's called. So the nickname is hitchhiker's thumb. So you cannot.
I can do it like.
I don't think you can either. Really, compared to like it like points backwards, right? So I have hitchhiker's thumb. Another genetic trait that really kind of doesn't matter is whether your ears are attached or not. Yeah, no joke. Whether your earlobes attach or are detached, that is a genetic thing. Another thing, which obviously we're all wearing masks, and in normal year, kids will start like doing this at each other, but is if you can roll your tongue, which I cannot, and I don't mean like a rolled R, like I mean roll like into a like tube, right? Like kind of into a straw.
Which way?
I think they really shove it. I might shove it.
Like roll your tongue like hot dog or like.
Yeah, like hot dog bun.
Like forward or sideways?
Yes.
Oh, my cousin
Either.
either clam tongue.
Yeah, things like that, right? Is like how much control you have of your tongue.
Yeah.
So let's say we want to track the probability of somebody being able to do and. They can roll their tongue and bend their thumb backwards. How did we say we're going to calculate and? Multiply, right? So if we do, let's hypothetically say half of people can and half of people can't, right? Let's just make our life easy right now. What's a half times a half? A quarter. Now what about if we say or? I want people that can bend their thumb back, like me, right? I can't roll my tongue, but I can bend my thumb backwards. Some of you probably could potentially roll your tongue. Yeah, so you'd be in the or category too, which is funny that there's two of us with how this table works. How would I calculate or? Add?
If any of them have yes.
Wait, for or, it's yes.
Because here, well, all of these are 1/4 boxes, right? Like each of these is 1/2 and 1/2.
If any of them have, if either of them have yes, so that would be 3/4.
So you said add, so add a half and a half? No. Wait, add what? A fourth and a fourth?
Yeah, because if you multiplied it, you could end up like getting more or less than like the total.
Well, it's 3/4 because it's if either of them have yes in it at all. The only
Is
one
that
that
what
doesn't is
we're
no.
Ooh.
Then we have to add them all.
So the or, so let's call this A, and let's call this B. So we said, you might want to write this down. This is now one of those math things. We said probability of A and B was a multiplication. Probability of A, really I should write P of A. P of A times P of B. And that was just fine, right? Like everything was good with that. There we go. And now we're saying probability of A or B. Well, what was the probability of A? Here we, like now? Yeah, so we did, but wait, if I do a half plus a half, that feels silly. I feel like that's too much.
I think it's P of A times P of B times 3. Or no, wait.
Yeah, but would that always work?
If it's an equal situation, then no.
What do I need to get rid? So here, this currently equals 1, right? Because a half and a half. That's not good. What do I need it to equal? We need to equal 3, 4. We're too big, so we probably do need to subtract something. What do we need to get rid of? So we currently we're looking.
What equals 1?
Overlap one. Yeah, yes. Yeah.
So what would we call that? We need to subtract this.
We need to subtract the opposite corner.
Yeah, that's what you said.
1 minus probability of.
You sure we need to subtract?
Well, if we're trying to calculate,
It's 1 minus
Wait, are we
probability of A times B.
like,
So P of A means yes, means it does happen. This is a yes. So this is yes plus yes, is what we're looking at right now. So we did yes plus yes.
So then we need to subtract the both yeses.
So we have this is at, no, that's B. If I follow my lead from earlier. And
then
this,
we can do the 1/4 that's blue. That's what we would need to make subtract.
Wait, so are we trying to figure out where
No,
it's
it's
just?
P of A plus P of B minus P of A times P of B.
ooh,
I'm
So
confused
yeah.
about what we're trying to figure out here. Are we trying to figure out which situations at least one of them is true, or which situations one of them is true and the other is false?
at least one of them is true. The probability of this or that. Which is allowed to have the and, but it doesn't need it twice. Is that a real O? Or like the I want class to move on O?
No, I understand now.
Okay.
We're doing the overcounting thing.
Yes, we're doing the overcounting thing. We're figuring out the rule.
Well,
We're doing it together because I don't know either.
Mm-hmm.
So minus P of A and B. Man, we need some better notation. I wonder if there's any better way to write these things. Okay, this is too easy.
We can do the easy stuff.
No. What is the probability that two people who randomly meet each other, I forget what the setup is here.
what's an Abaja?
Navajo.
Whatever.
It's a,
Whoa, not whatever. American Indian tribe. Oh, yes.
Oh,
So
yeah, Navajo code talk.
let's say we go select two people from the Navajo tribe. The probability of their blood types is what is shown here, which is interesting. So Navajo are American Indians, and they were, the original people here, essentially. They only have two blood types. They don't have type B because they were a small collection of people and only ended up with type O and type A. So if you are 100% Navajo, you'd only have one of these blood types. What's the probability? Actually, just fill this whole
wait,
thing.
typo is more common. Whereas
No, for Navajo people,
very uncommon for
right?
local population.
So let's solve these things then. What's the probability both of them are type O? Both of them are type A. One of them is type O. One of them is type A. So we've got two ands and two ors.
73 squared over 100 squared. I don't really have to do it. Well, that's what the O and O is.
I've got 8 minutes that I could awkwardly stand here and just stare, waiting for you to calculate things. And Jake's got a calculator at least.
I do, yeah.
Or we could just sit here and not do it all.
How long do you want to awkwardly stare at each other?
This could be sit and awkwardly stare class. That should be our new Phoenix class.
I got 532. Yeah, 5329.
Hey.
Yeah, I got that too.
Oh, I did it without a calculator.
Wow.
Did you do 73 times 73 without a calculator?
Yeah.
Yeah, good work. So wait, that's
It's 0.53.
I think I just heard Mr. Hall say damn. So 0.5329. That goes where?
Oh.
Because these boxes are not equal size now, right? We all can agree that this is just a diagram.
Yeah.
I just have to say it out loud to make sure that we've all, and it's being recorded, so who knows if somebody stumbles on this video.
We want to make sure that they can do the math correctly.
Right. How do we get out here?
Oh, I didn't calculate that. I got the double A one.
I'm gonna change colors to make sure. You got double A? Okay.
Yeah,
What is that?
Double A is 0.0729.
0.7.
29.
So really, if we're doing percentages, this is like 7.3%.
Yeah.
And this is like 53%. Let's just go ahead and lean into this and do percentages. 53%. This is going to be like 20%. I'll tell you it's 19.71%. We'll go ahead and give it the 10th spot. Why am I making these the same color? Yeah, they're the same result, right? One of them O, one of them A, or one of them A, one of them O. It's like rolling a 3 and a 4 versus rolling a 4 and a 3. Right? They're the same result, but different.
Swap.
Yeah. So they're the same, but they do count as two results, right? O and A versus A and O. Okay, so we said we know mathematically how to figure out the OR by doing the plus minus the and. So hypothetically, we said 0.27. So if we want to say what's the probability, one of them is A. You guys are getting lost in my posters.
Yeah, I'm very confused.
Let's practice calculating. Well, a couple of us. I don't know if you have your calculator. 0.27 squared, because now that we're taking shortcuts for the probability, so 0.27 squared gives me boom and boom. But that overcounts this box. So then we need to subtract away. So minus
0.27.
No, 0.073. I'm still lost.
Well, it would. Wait, what?
I'm giving you time to try to get unlost.
I've
The
been
thing
lost
is
the whole
0.27
time.
squared. Wait, why are we trying to calculate? The thing of the box?
I love these moments because it at least makes you curious. What is the probability one of them is type A? So both of them are allowed to be type A.
No, it's 1 minus the probability. 1 minus 0.73 squared.
Why don't you just add the percentages together?
If we add the percentage, so wait, 27%? So 0.27 plus 0.27?
No, it's 47% that one of them is A.
I got 54 though, because I did 0.27 plus 0.27. Ooh, the minus. The subtraction. If we do 0.27 plus 0.27,
Minus 0.27 squared.
that's A plus A, right? That's blood type A plus blood type A, but the problem is we did this twice. So then minus 0.27 squared. All right, so it's 0.27 plus 0.27, or 27%.
Or you could just do 1 minus.
We could, but
0.73 squared.
But what if we're practicing for when we don't have this model and you don't want to draw the rectangle because you're like 8th graders and you'll be like, I can just use my calculator. That's why I'm trying to get you to practice this. So that minus 0.27 squared, 0.467.
I got 0.01 less than that because I used the actual value.
Ooh, flexing. I use the actual value.
Although I did the 19.7, but also so I didn't actually use the actual.
You are in.
All right.
Correct.
So now, here's your challenge. I want you to write down what you think you need to write down. We are going to keep us until 12:18 to give Perry kids a little bit more time to clean up and get out of the cafeteria so we don't overlap so much because their lunch is super short compared to ours. So we've got...
The equipment to do a blood transfusion.
I love this class so much. You're totally not listening to what I'm saying. We have like 4 minutes. So, important information. For some reason, you're traveling with people from Vermont.
Cool.
45% of people have type O. Well, here's your, because we literally just discussed this, of how many people have type O. Yeah, so it's less common in just general people.
Or
When we
that
just,
type of
Well, in Vermont.
write this down. Write this down. Because then you're probably going to need to make a model because we have a lot of pieces here. 40% have type A. 11% have type B. I don't know what color to use. Orange. 4% have type A.
So Zach doesn't have AB.
So, yeah, let's play out these probabilities. Let's make one of those area models. Let's be able to tell Zach just the straight up truth. Hey, buddy, here's your chance that you have AB blood and somebody else has AB blood. And, well, that's not very good. So if you have AB blood, things probably don't look very good. So, like, we know it's 4% chance that he has AB. But if he has AB, what's the chance somebody else matches him?
4%.
But
If it's given they have AB.
but what is that? 4% of 4%.
Well, no, because someone else's blood type isn't dependent on your blood type. It's still a 4% chance.
So I'm probably setting this up poorly. Here's what we want to do.
Yeah.
Because, and this is probably what I should have explained. And maybe you know this, Connor. Why is O blood type desirable? Like, I have O blood type. I just...
It works for everyone.
Almost.
Oh.
Oh, wait, yeah, you guys are right.
Yay!
Okay, positive and negative sort of come into play, but we're not worrying about that in this problem. So we're going to say it works for everyone, even though positive and negative comes
Why did
into
they
play.
have to make this all
Is it like O positive and O negative, and
Yes.
O positive works for
Yes.
all positives and O negative works for all
O
negatives?
negative is universal donor. O positive,
universal receiver?
universal receiver, something like that. But also, like A and B can take O positive, but AB can't. Something I forget. It's complicated.
Yeah.
So tomorrow we will pick up by calculating all of these different probabilities.
Yay, math class! This is such a great
You guys just yay like we're like a bad cartoon show.
So if either of them have O.
Thank you guys.
If either of them have O, then Zach is good.
semester Hudson.
According to this premise, yeah. If either of them have O, or well, no. A, B,
Nick has O.
O is not a universal receiver here because they're not overcomplicating this. A, B is a universal receiver. So if Nick has O, you guys can come on in. We're just still Aiden. You guys can come in. If Nick has O, we're good. If Zach has a B, we're good. But then we gotta talk about the other things. And I gotta chase you. Oh, I don't really have to chase you out of here, actually. But I want to go outside and eat, so there's that.